So basically the topic here is we want to understand what can we say about Fourier coefficients of multiplicative functions when we look at them in small intervals. Or more precisely, you have some multiplicative function defined over a large interval, and you take a randomly chosen small interval inside this big interval. The question is, can you guarantee that almost surely the restriction of your multiplicative function to this small interval has no large Fourier coefficients? So this is the problem we will discuss and some recent progress on it, but it is intended as a colloquium talk for a general audience. So large part of the talk will be devoted to explaining how this connects to some other central problems in multiplicative number theory, and how these in turn are motivated by fundamental arithmetic questions concerning the distribution of prime numbers. So let us begin. As I said, this will concern general multiplicative functions, so let's quickly recall the definition. These are functions from the natural numbers to the complex numbers, such that their value at m times n is equal to their value at m times their value at n whenever m and n are coprime. And although the things I will discuss will concern general multiplicative functions, both for concreteness and due to its central role in the story, we will focus much of our discussion on the case of the Liouville function. So at some point in the talk, I will tell you exactly under what conditions on multiplicative functions these results and conjectures should hold in general. But I want to focus on the Liouville function, both so you have something concrete to think about, but also because it is the motivation to understand this function behind these conjectures that we will discuss. So let us also recall its definition. So the Liouville function is a function from natural numbers that takes two possible values, -1 and 1. That is given by lambda of n is equal to -1 if n has a known number of prime factors counting repetitions, and lambda of n is equal to 1 out of 3. So first values, lambda of 1 is 1, lambda of 2 -1, lambda of 3 is -1. In general, lambda of p will be -1 for every prime p. And then lambda of 4 is equal to 1 because although 2 is the only prime divided, 4 divides it twice, and we are counting repetitions. Yeah, so we'll be mainly working with this function. And one thing you can immediately notice from its easy definition is that the Liouville function is not just multiplicative, it's in fact what is called completely multiplicative. So lambda of m times n is equal to lambda of m times lambda of n for every choice of natural numbers, not just when they're coprime. But this also makes it simpler to think about some things that we'll talk about later. And so the motivation why we care so much about this function, the Liouville function, is because it's very well known that the distribution properties of this function are very tightly related with the distribution properties of the prime numbers. So it's a classical fact. The distribution of prime numbers is intimately tied to the statistical properties of the Liouville function. And the most classical example of this is given by the Riemann hypothesis, which in one of its many equivalent formulations says that given any epsilon greater than 0, we can find some constant that depends only on epsilon, such that if we look at the partial sums of the Liouville function from 1 up to x, and we look at its absolute value, then this should be bounded by this constant times x to the 1/2 plus epsilon, and this should hold for every positive real number x. So of course, this is also equivalent to getting an essentially optimal estimate of the error term of the number of primes from 1 up to x. So as you see, it's a very tight relation between the Liouville function and the prime numbers. Estimating the sums from 1 up to x is essentially equivalent to counting how many primes there are from 1 up to x. And usually you may have seen this kind of things usually phrased in terms of the Moebius function, which is a close sibling of the Liouville function. Is function that is a Liouville function when n is square free, and if I square divides n, then it's just equal to 0. And the Moebius function is in reality the one that arises naturally, so to speak. But essentially anything that one can prove about the Moebius function will prove the same statement about the Liouville function or vice versa. And the Liouville function has some technical conveniences, like the fact that it's completely multiplicative, not just multiplicative, like the Moebius function. And it always takes absolute value equal to 1, since the value 0. So it's things that are slightly technical conveniences, and that's why lately in this kind of things, it's kind of a convention to use the Liouville function instead of the more classical Moebius function. And one thing you may notice from this estimate is this is the kind of boundary we would expect to have if the Liouville function was just a random function that took its two values, 1 and -1, with probability 1/2 each. And indeed, that will be a topic throughout the talk, the sort of random behavior of the Liouville function. Now, although this is the most classical example, this is by no means the only way in which we have a tight relation with the Liouville function and the distribution of prime numbers. In fact, other famous problems about primes, like Goldbach conjecture or the twin prime conjecture, will follow from a sufficiently strong quantitative answer to the following well-known question from the 60s. So this is Chowla's conjecture that goes as follows. So for every choice of distant integers, 1 for each k, we expect that the limit of this expression should go to 0 as x goes to infinity. Well, what we're looking at is the average value of the sum from 1 up to x of the Liouville function evaluated at n plus h1 times its value at n plus h2, so on until n plus hk. So this expression should go to 0, and this is, of course, we're looking at the sort of self-correlations of the Liouville function and certain shifts. And studying this kind of self-correlations is a typical topic for a lot of functions of arithmetic interest. In particular case of the function, if we had a sufficiently strong quantitative answer to this question, not just that it goes to 0, then that should be enough to deduce these questions about primes. So what do I mean by a sufficiently strong quantitative answer? So if you look at the Riemann hypothesis, what we expect is a really strong estimate. We are claiming square root cancellation, which is essentially the optimal thing that we can expect. Here, in fact, it will suffice with something much weaker than that. We don't even need a power saving in the bounds. What we will need to have is, if you look at this, the sum, each term is bounded by 1. And the sum, so the trivial bound is x. What it will suffice to have is a bound on the form x divided by a large power of a logarithm. So we will just need to save a large power of a logarithm over the trivial bound to get the applications, which is a relatively weak bound. Of course, we don't even know it goes to 0 yet, but so it's not something that we expect to prove. But in principle, it's a much weaker kind of estimate. And even without this connection, this is a conjecture that is interesting by its own arithmetic context. If you think about it, what it's telling you is that in a certain sense, if you pick us, for example, some fixed integer h and you shift by that integer, you essentially lose all information about the multiplicative structure of your natural number. So concretely in this case, the point of this conjecture is more or less that if you know the value of the Liouville function at n, that doesn't really tell you anything, any way to predict the value of the Liouville function at n plus h. And the same for these general patterns. So of course, this statement is again an assertion about the random behavior of the Liouville function, the independence of its different values. And indeed, as I said, in general, we expect the Liouville function to exhibit pseudo-random behavior. So in the sense that its statistical properties should be similar to those of a random function that takes the two values 1 and minus 1, each with probability 100. So of course, by pseudo-random, we just mean that the Liouville function is defined deterministically. Look at cheat a little bit and look at some statistic that depends on the way the Liouville function is defined. But as long as we're not cheating and we're looking at some genuine kind of statistic, we generally expect this essentially sort of similar statistic and also a random function that takes these three values each with probability 1/2. So it's easy to know what to expect with this function. One particular consequence of this that is very relevant principle in analytic number theory is that in particular we expect that we have sums of this form. Then they should exhibit cancellation whenever f is a simple or a deterministic function. So although we don't really know what we mean by simple, this is a very useful principle in analytic number theory. Both because lets you know what to expect in other situations, but also because it goes to the core of the issues we have with the problems about prime numbers that I was mentioning before. So one consequence of this principle that was observed by Selberg in the 40s, so a very long time ago, is that because of this principle, what is one of the main tools we have for the last 100 years to study the prime numbers, which is sieve theory, can never really succeed in proving the results that it was created to prove. So the simple observation goes as follows. From a modern terminology, sieve theory is the idea of trying to approximate the primes by a simple function. So more precisely, the characteristic function of the primes by a simple function f. Now, if you think about it, this is clearly telling you that that can never really succeed. Because if you had such a function, then this function f should be essentially 0 when n is not prime, so it would be essentially 1 when n is prime. It's a simple function approximating the primes. But the Liouville function is always minus 1 when n is prime. So essentially every non-zero term of the sum will be minus 1. And then, of course, there will be no cancellation, contradicting the spreads. So this very simple observation, again going back to Selberg's parity problem, slightly different form, tells us very clearly that sieve theory can never really succeed, at least by itself, in solving this kind of problems that I was mentioning before about the primes. But of course, that hasn't stopped people from using sieve theory, because there are other things that you can prove. So for example, this tells you that you cannot use sieve theory to prove the twin-prime conjecture, that there are infinitely many primes key, such that p plus 2 is also prime. But it doesn't prevent you, for example, from proving that there are infinitely many primes p, such that p plus 2 is the product of at most 2 primes, which is Chern's theorem. And the reason, of course, is that this does not give you any obstruction to getting a simple function that approximates the numbers that are the product of at most 2 primes, right? Because when n is prime, the Liouville function is -1. When it's the product of 2 primes, it's equal to 1. So in principle, there could be cancellation here. And indeed, it is in some sense possible to do something like this, and that's why we have Chern's theorem. And similarly, this is a reason why you can prove Chit-Saint's theorem that there is some constancy such that infinity with primes p, such that p plus c is prime. But you cannot say exactly what this constant is, because you can easily do an argument like this to get a contradiction with this principle. On the other hand, the interesting thing is that if we could actually, we don't have a definition in general what simple is. If you could actually prove a rigorous version of this principle, then you could input that into the sieve theory. But actually prove it. So the nice thing about this easy observation is that it goes very much to the core of what's the conceptual issue with these problems. So we don't have a definition of what a simple function is, but Peter proposed a definition of what a deterministic function is. So one gets this intensively studied problem, Sarnak's conjecture. So of course, when you view, it's very well know about this, but let's make sure we're on the same page. So let me talk a few minutes about this. So the conjecture goes as follows. So let T be a continuous function of zero entropy on a compact metric space. Then the claim is that for every fixed complex valued function on the space, continuous function, and every initial point on the space, we should have cancellation in the sum. So if you look at the limit as x goes to infinity of the average value of the sum from 1 up to x of the Liouville function multiplied by f evaluated at t to the n of y, then this expression should go to 0. So what is going on here? We have some space, big y, a point, little y in space, and some zero entropy transformation. So we take y and we apply t successively, getting an orbit. And then at each point of this orbit, we evaluate our fixed function f, getting a sequence of values. And the conjecture is that as long as t has zero entropy, then the resultant sequence cannot really capture the behavior of the Liouville function. Anything that is built on this form will cancel out in the sense when we look at its correlations. So the key assumption here is that of zero entropy. So loosely speaking, the zero entropy condition means that in some statistical sense, we can predict the nth value of the sequence that we create in this way. So as long as the transformation has zero entropy, any sequence created in this form will have the property that we can essentially predict the nth value of the sequence from knowing some fixed set of previous values. We have this deterministic behavior. And of course, as I said, the Liouville function should behave randomly. We expect exactly the opposite of this. So in particular, nothing that is built in this way should be able to imitate in any meaningful way the behavior of the Liouville function. And in particular, you should get this kind of cancellation for these sums. So as you see, you get this way to formalize the principle that I was talking in the previous slide. But this question has a few practical advantages. One of which is the fact that it's formulated from the point of view of dynamical systems. So a nice consequence of that, of course, is that it gets a lot of people working on dynamical systems interested in these things. And if you actually think about the kind of things that we want to know about the Liouville function, they certainly have a certain dynamical flavor to them. So it's kind of a fruitful interaction to have. And then there is another practical aspect to it that is a problem that we can say something about. If you look at Chowla's conjecture, it was formulated in the 60s, and for more than 50 years, we haven't been able to really say much about it. There's no non-trivial case of this problem that is known. On the other hand, there are a lot of zero entropy systems. So there are some systems that, we can relatively easily prove this for them with things that we know for a long time. There are others that, takes a bit of effort, but you still can do it. Others where it has required some new idea to prove those cases. And of course, there are many cases where we don't know. So it gives you a continuing spectrum of problems, which of course is very convenient. You're trying to understand better the Liouville function, because you can actually try to localize what's the next particular case that is right at the border of the things that you actually know about the Liouville function, and try to work from there. Now, of course, the objection one may raise about this is there are a lot of zero entropy systems that's knowing whether the Liouville function correlates with the most exotic of the system really add you anything relevant about the arithmetic content of the Liouville function. And there actually is a concrete answer to this in a sense, which emphasizes what I was saying before, which is, that Chowla's conjecture implies Sarnak's conjecture. And this is indeed something very easy to see. And, what this is telling you is that if you want to solve the questions about the primes that I was mentioning before, or if you just care about Chowla's conjecture by some arithmetic content, then you kind of need to be able to deal with every single one of these zero entropy systems. And also emphasizes the fact that, Chowla's conjecture we haven't been able to say anything about. So this kind of builds a bridge where we can, look at the continuous spectrum of difficulty, trying to build our tools towards Chowla's conjecture. So I've been telling you about these different problems about the Liouville function. And I will tell you one last one, which is the one that I mentioned at the beginning of the talk. So these are the uniformity conjectures. And in particular, I will concentrate on the particular case, which in a sense is the central case, which is that of the Fourier uniformity conjecture for the Liouville function. So what do we have here? The hypothesis, we have some function h of x. And the only thing we ask of this function is that it goes to infinity as x goes to infinity. But it doesn't matter how slowly it goes to infinity. This is the crucial thing. So in what I was telling you before, so x will be the size of our big interval, and we will see what happens inside small intervals of size h. But again, what makes this problem really hard in a sense is that h can grow as slowly as you want. So it's really small intervals. Then the conjecture now is again that an expression of this form goes to 0 as x goes to infinity, where now what we're looking is at the average value of the integral from 1 to x of this in here. So what we're doing is for each point little x in our integral, we're looking at the interval that goes from little x to little x plus h. And we're looking at the maximal size of a correlation with the Liouville function with an exponential in that interval. So we're taking the supreme over all possible frequencies alpha. So this choice of alpha depends on x. And we look at the maximal size then over any choice of alpha, the correlation of the Liouville function with e to the 2 pi alpha n on this interval. So in a sense, what we're doing is we're trying to approximate the Liouville function in the following way. We try to approximate it on the big interval x by in each little interval in this big interval, choosing the frequency that behaves the most like the Liouville function. So we're allowed to change the frequency at each point. And the conjecture is that even if we do that, even if each interval we choose the best frequency, we still cannot approximate well the behavior of the Liouville function. It still goes to 0. Or if you want, in the way that I phrased it at the beginning, if you pick a randomly chosen small interval, then almost surely the restriction of the Liouville function to that interval has no large Fourier coefficient. And of course, again, this is an assertion about the randomness of the Liouville function. This, of course, is a very basic Fourier analytic combinatorial fact that a function having no large Fourier coefficients in many respects behaves like a random function. So, studying these correlations with the exponential functions is a very classical topic. In general, Fourier coefficients of multiplicative functions are a classical topic, but in a particular case of the Liouville function, this goes back to work of Vinogradov and Davenport almost 100 years ago. But to keep in mind, what makes this particular problem particularly hard, is that two things. One, h is arbitrarily slowly, which is something that until recently we didn't know how to say anything about. And the fact that we are allowing the frequencies to change. So this is a good time to tell you in what generality these things hold. So I said at the beginning, this is not just for the Liouville function. These things should hold in general for any multiplicative function under some very general conditions, which are as follows. So the condition that we need is that, well, g is bounded. One. And the thing is that all these things that we've been discussing should hold as long as g is not essentially of this form, or the form n to the it chi of n, where t is some small real number and chi is a Dirichlet character of small modulus. So you can essentially think about it for the stochastic periodic multiplicative function of small p with chi. And these functions that are of this form have a name. They are non-pretentious multiplicative functions. It was a terminology introduced by Granville in some direction around 20 years ago. And they have a name because they indeed play a distinguished role with respect to multiplicative function. They sort of play the role of multiplicative characters in this context. And they tend to be the abstraction to randomness in the behavior of multiplicative functions. So in particular, for example, they don't satisfy the estimate that I just mentioned. If you replace the Liouville function with something of the form n to the it chi of n, you don't get that it goes to 0. But the conjecture is that as long as your function does not look like some of this, you can tweak these functions a little bit and get essentially the same. But as long as you are not very close to these functions, then indeed any multiplicative function that is not non-pretentious should have the previous expression go to 0 in the same way as the Liouville function. And indeed, in fact, all the conjectures that we are discussing in this talk are expected to hold under an assumption of this form. Well, except the Riemann hypothesis, but the Sarnak, Chowla uniformity conjectures should hold for any non-pretentious multiplicative function. So this is one generality, and there's a further generality for the uniformity conjectures. So we have what we could call the full uniformity conjecture, which predicts that once you have the same result that I stated before, both for real function and for non-pretentious multiplicative functions, if instead of taking the suprema over all the exponentials, we take it over more general objects that are known as nilsequences of bounded complexity. So I will not give a precise definition, but let me remind you verbally of what these things are. So nilsequence is essentially a flow arising in the same way as in Sarnak's conjecture. It has some space and some transformation in the space, and some fixed continuous function. So it arises in the same way. Nilsequences correspond to the particular case in which the space is of the form G mod gamma, where G is a nilpotent group, essentially nilpotent group, and gamma is a discrete concompound subgroup. And the transformation in the space is given by multiplication by a fixed element in this group. So if you have that particular case of the kind of flows I mentioned before, what you get is a nilsequence. That's the definition, almost. And so in particular, they generalize the exponentials. So the exponentials arise in the particular case where G mod gamma is R mod C. And the conjecture is that if I take the supremum over all these nilsequences, instead of just exponentials, I should get the same state. And so the question is, why do we care about nilsequences? And this, again, another well-known thing that I'll quickly remind you. The thing is that, going back to starts with work on Gowers and Semedory's theorem and corresponding work of Hoss-Kraj and Godic theory and the Green-Tau and Green-Tau-Ziegler theorems, that tell you that, roughly speaking, if you have a function and you want to know what its statistical properties are with respect to independent linear forms, so you evaluate your function along independent linear forms, you look at the resulting statistics. Essentially, what we now know is that the only way in which this behavior with respect to these linear forms can be different to that of a random function is if the function actually correlates with a sequence. So it's actually the only way in which you don't get this random behavior is if in fact you have an explanation for it, which is that you have correlation with random sequences. The only way it can happen. So it's an elegant and general state. And so, of course, that's the motivation. If you can actually prove the same statement that I mentioned before, but instead of taking the suprema over the exponentials over all general sequences, what you're getting in conclusion is that if you look at the randomly chosen small interval, and you get some non-pretentious multiplicative function like the Liouville function, then on a randomly chosen interval, your function, the Liouville function, say, will behave like a random function with respect to independent linear forms. Almost surely on your chosen interval, which of course is a very strong statement, and this is what motivates the problem. However, we shall focus for the rest of the talk on the Fourier uniformity case, both for simplicity, but also because it is largely expected that any proof of this particular case should extend with sufficient effort to deal with the general case of nilsequences. So when the relevance of nilsequences was observed, there was a lot of work extending results from exponentials to nilsequences. By now, there's a big machinery to do this. But it doesn't mean that it's easy to do it, but we have a blueprint on how to do it. Even in the case of the Fourier uniformity conjecture, we had results that have been extended. So we expect that while it's not easy, the real difficulty lies in the Fourier uniformity case. We don't know how to deal with arbitrary small intervals. There's a really big part of the problem. So we'll focus on that case. So I told you about these three conjectures, Chowla, Sarnak, and uniformity conjecture. And of course, the point is that they turn out to be essentially the same question, the three, in the following sense. So precisely, it was shown by Tau that the following statements are equivalent. We tweak them a little bit to become equivalent. So what we do is take Chowla's conjecture and apply what we will call a logarithmic average. Look at a logarithmic weight version of this conjecture, where we have the same hypothesis. We have some integers h1 to hk, and we look at the self-correlations and exactly the same as before, the sum of 1 up to x of lambda related to n plus h1 times the 1 to n plus hk. The only difference that we have now is that we are adding a little weight of 1 over n. So to each term, we add a weight of 1 over n. And since the sum of 1 over n from 1 up to x is essentially log of x, the correct normalization is to divide by log of x. So maybe it's worth pointing out that this kind of averages are not an entirely strange thing. They're kind of a classical thing in analytic number theory, which is not hard to, at least in the more multiplicative nature problems, it's not hard to justify from the point of view of Dirichlet series. But if you look at this particular case, then what you get, which Chowla conjecture implies this, then this resulting conjecture does not only imply the corresponding version of Sarnak's conjecture, but it actually turns out to be equivalent to it. So you take Sarnak's conjecture, exactly the same hypothesis, T a continuous function of zero entropy in a compartmented space, some fixed complex valued function f and some initial point little y. And again, you look at the correlation of the Liouville function against f to t to the n of y. And the only difference again is that you add this little weight of 1 over n and normalize by log of x. And then you get that this version of Sarnak's conjecture is not only implied by the corresponding version of Chowla conjecture, but it turned out to be equivalent. And not only that, but both statements are equivalent to doing the same thing to the uniformity conjecture, which again, h, arbitrary slowly growing function of x. And you look at the limit of this expression, the same as one as before, where the only difference is that for the interval that starts at little x, you are adding a weight of 1 over little x. And what is similar if you replace the exponential functions with the sequences of bounded complexity. And in fact, in this particular case of the logarithmic averages, there's one nice advantage for the case of the uniformity conjecture, which is that this was shown later by Matomaki-Radziwill, and Ziegler, that in fact, in this case, we don't really need to go to arbitrary small intervals, which is, but in fact, if you can prove that for every epsilon greater than 0, the conjecture holds with h equal to log x to the epsilon, then that kind of self-improves. So once you can prove that, you can deduce from that that it holds for an arbitrary slowly growing by value of h. And that in turn implies that it holds for the Chowla and Sarnak conjectures as well. Those conjectures. And this is very convenient because indeed, as I said, the big problem here is that we don't really have many tools to deal with arbitrary small things. So it's very convenient to have a bound on how far we need to go. On the other hand, of course, log x to the epsilon is still very small from the point of view of the classical analytic number theoretic techniques, but at least we have somewhat some work to do. So we get that these three problems are equivalent. And another thing that is, I think, worth pointing out about those things is that it's not clear how much simpler these versions are. The original conjecture. You're still kind of keeping the core of the problem in all the cases when you do this averaging. And it's, I've been trying to motivate in a way that, maybe it's natural that the three problems turn out to be very related to each other. But of course, it's nice to think that they represent, in a certain sense, different directions in analytic number theory around the Liouville function, correlation with exponentials. So it's a classical thing going back to binaural and Davenport. If you look at Sarnak's conjecture, the relation with number theory with dynamical flows is maybe more recent, but still you take it so. And then you have Chowla conjecture, much more classical statement with the parity problem, that kind of thing motivated by the twin conjecture. And all these kind of directions converge to these things. So in a sense, there's one thing we don't understand, we should explain all these three statements. Now, if I was giving this talk 10 years ago, of course, people working on this, it's really nice, these three things are equivalent, but the problem is that we can't really solve any of these three questions. Now, 9 years ago, that situation changed, in a sense, let me argue, because of this following fantastic result of Matomaki and Radziwill. So they made this result that, in a sense, is a game changer for these kind of problems, which is that, so as before, so you have some function h that depends on x, and the crucial thing that is really stunning is that you ask that it goes to infinity with x, but you don't care how slowly it goes to infinity with x. And so what they show is that under this very, very mild assumption, this expression goes to 0. So what you're doing is looking at each interval size h of the partial sums of the Liouville function in that interval. If you take the absolute value of each partial sum, then this expression on average goes to 0. Or in the way that I phrased before, if you look at a randomly chosen small interval size h inside the big interval size h, that almost surely you have cancellation in the partial sums of the Liouville function. And the same holds not just for the Liouville function, but for general non-pretentious multiplicative functions. So this is a remarkably strong statement, because before this we really didn't have any way of dealing with things that happen in arbitrary small intervals. It was something that was more of a fantasy. And of course, because of what I was telling you so far in the talk, it's really important for us to understand what happens in arbitrary small intervals. So this is a really, really strong result. And in fact, even in the original article, they showed how you get some consequence from the, say, Chowla's conjecture. So in the case of two integers, so say, for example, lambda of n times lambda of n plus 1, you want to estimate that. Well, they cannot show that on average it goes to 0, but they were able to show that the absolute value is the limit is strictly less than 1, have some cancellation. And, not long after, Teretao used this result to prove the particular case of the logarithmically average Chowla conjecture, the case of two integers that prove that case. Now, since this result has been a lot of work on this question that I was mentioned before, because in a sense now it makes sense to try to think about it, now we have this information. But the reason why we haven't been able to succeed in a sense is because the methods behind this depend in a very delicate manner on the multiplicative structures. It's really a multiplicative number theory. So Well, if, for example, you look at the uniformity conjecture, well, what you're doing is trying to see what happens when you twist the Liouville function by some exponentials. When you do this twist, you, in a sense, automatically kill this multiplicative structure. And the methods are, in a sense, so delicate to this multiplicative structure that even if you do something, just a little twist, you kind of lose all the tools that are behind this, this result. So that's the big problem, and not find a way to adapt the methods to a more general setting. But we now have this piece of information, extremely strong piece of information. We know that we have cancellation not just of the Liouville function, but of any non-British multiplicative function on almost every interval. And of course, it makes sense now to see what one can do about with it. In particular, there's a sense in which the uniformity conjecture is a nice of the three equivalent problems to want to think about at this stage. One, because it's, as you see, it's the most naturally similar to the statement. But also, in a sense, although the three problems are equivalent, when you do you prove the equivalence, in a sense, the uniformity conjecture is the weaker. The hardest part is to prove that the uniformity implies Chowla. Because it makes sense to think about the uniformity conjecture. So in the last part of the talk, I want to tell you about some work last year regarding the uniformity conjectures, which in particular, I think it will be useful to clarify what's the current situation in general with these three equivalent problems. So as before, we let delta be a function of x that goes to infinity with x. And again, it has an arbitrary slowly growing function of x. And so I'm going to give you two results. Let me tell you beforehand that this is the second result that is the deepest. I was finished here at the institute. So the first result is the best bound we have now in the Fourier uniformity conjecture. So it says that the Fourier uniformity conjecture holds whenever h grows at least like e to the log x to the 1/2, essentially. Not slightly more than log x to the 1/2, but essentially log x to e to the log x to the 1/2. So I guess in this kind of statements, the first thing to say is whether it is a natural bound. And indeed, it is a natural bound for this problem. In the sense, for example, that even before this result was established, it was known that, if we did anything that looked like the tools we had before, this is the absolute limit we could achieve. Things break down very dramatically at this e to the log x to the 1/2 variant. And in fact, one interesting thing is that this limit appears not just in this problem, but in many related problems, which, in each case it has a somewhat different explanation, but in the end, it always comes down to the fact that you'll have some sort of iterative argument that starts with things of size h and ends with things of size x, kind of squares at each step. And if you do an iterative argument of any shape in this kind of things, and you naturally lose a factor at each step of your iteration, then these things is here where they accumulate to a thing that is too big to the error term that you accumulate is too big and destroys your argument. So there are a lot of things that break down right here, and I will say something else about that in a second. But of course, there were things that broke down before. And in particular, so the first result about Fourier uniformity is due to Matomaki-Radziwill and Tao. So what they show is that this holds when h grows like x to the epsilon for any epsilon greater than c. And in their proof, a crucial ingredient is to get estimates for exponential sums of the primes. Now, these estimates for exponential sums of the primes, the best range they are known to hold will correspond to e to the log x to the 2/3, which is follows from the best bound essentially we have on the prime number theory, which is work of Pinot-Gradov and Corbeau from 60 years ago. So it's not something that we expect to be able to improve in the near future. Now, in fact, they didn't really need cancellation in this exponential sums point-wise, as is implied by this. But what it is an average version of this cancellation. And in fact, so in subsequent work of Matomaki-Radziwill, Tao, and Ziegler, they show that this average version of cancellation in exponential sums holds in the range e to the log x to the 5/8. So they were consequently able to improve the uniformity. They don't range the uniformity conjecture to e to the log x to the 5/8. And so in this approach, it kind of proceeds from a different strategy. So in essence, the beginning and the end are the same as this previous work, but it's the middle, which is the key part in a sense, is done in a very different way, which turns out to be actually substantially simpler. And the key point, one of the consequences of observation that in fact, at least in this range, you don't really need to know anything about cancellation and exponential sums over primes. So you can deal with this range without any information about it. And so as I said, it's not the only problem that has a natural limit at e to the log x to the 1/2. And there's one that is very related to this that I think is worth mentioning. That is the work of Helfgott and Radziwill. So recently, Helfgott and Radziwill established some very interesting general results that a particular consequence they have, and in fact, kind of motivates the result. It's more or less as follows. So this is roughly speaking. But remember that I mentioned before that we don't really need to go, at least for the average case, the logarithmically average case, we don't need to go to arbitrary small h. It will suffice to prove it for h equal log x to the epsilon for every epsilon greater than 0. So of course, a natural way one will try to prove this uniformity conjecture is to push down as much as you can the range where you know it and push up as much as you can the range where you need to know it. So what they Helfgott and Radziwill will show is that one roughly speaking will say, like in a particular case of this general thing, that you can indeed improve from below the range where you need to know the conjecture. And in fact, the natural limit for their method from below is also e to the log x to the 1/2. So, you have the natural way to try to push down the range push up the range where you need to prove it. But it seems like in both directions, e to the log x to the 1/2 is the key point where you need to go. So what this result is, it doesn't show you that you can get right up to there, but you really need something very different if you want to break this. And this motivates why the second result is the deeper result, as I said, which is that assuming the generalized Riemann hypothesis, you can actually break this barrier. And in fact, you can break it rather dramatically. You can push it down all the way to a power of a logarithm. So of course, assuming GRH is a strong thing to assume, but the key thing behind this is that it's giving you sort of an explanation or a strategy of how you could actually break this barrier, so to show what is the structure that is behind these things that you can actually use.
To generalize this means for Dirichlet count.
For different functions. And so assuming GRH you can break this, you have some way of doing this. And perhaps it's also worth mentioning that the uniformity conjecture, one nice thing it had is that it had like three things we really didn't know how to do, three main abstractions to this problem. And what the approach behind the second result does is to show you that at least two of these things can be solved unconditionally. So it kind of says there is one specific thing that we don't know how to do in these problems. And for that thing, if you assume GRH, you can deal with it at least in this range.
I mean, just for the general audience, it's not at all obvious that GRH is good for lambda n, but it's not good for lambda n times anything else. So this is not, these are apples and oranges. Just so he's not assuming in any obvious way what he's trying to prove.
So as I said, the approach manages to reduce the obstacles we have to just one thing. There's one thing that kind of pops up in different parts of the argument, and the one thing that's missing from establishing the three wavelength problems I mentioned before. And hopefully at the end of the talk, I'll finish by telling you exactly what this abstraction is. And so, and another thing that is worth mentioning is that you use GRH to get the average exponential sum over prime cancellation that I mentioned earlier. And whatever range you can prove that cancellation on average, you will immediately deduce from this approach the corresponding bound. And as I mentioned, there are some bounds that are natural for these things. For example, the Vinogradov bound we don't expect to break. But the average bound that they have used for this, which gives you the range e to the log x to the 5/8, there's not really a natural. It's not something that you have a reason why that should be the limit. It's very plausible that one could get a better version of that argument, for which before there was not much of a motivation because we had this sharp barrier to the log x to 1/2 by other reasons.
What are you talking about? Karatuba or something?
What?
What's the 5/8?
So that's when you get cancellation on average over the.
No.
The zero provision gives you the pointwise bound, so that you don't have
on average.
But you only need this cancellation on average, which as I said, the bound one has nowadays is not something that is like clear why that should be the bound. So there's a chance that one could actually just improve that, and now that we have a way of translating that directly into a property of the uniformity conjecture, one should actually be able to unconditionally break this crucial barrier. So, and one last thing is this is for the original form of the uniformity conjecture. It's not the average version, but of course it implies the average version. And so let me give you one last statement about the Liouville function, which is very elementary. And I think it's very useful in understanding what's, the progress that's been happening in the last 10 years on these things. So given a natural number k, let us write s of k, so sines of k, for the number of length k sign patterns that are realized in the Liouville function. So these are the sequences of 1 and -1 of length k, for which that are actually realized as consecutive values of the Liouville function. So for which there exists some in natural number m, such that these are the values of the Liouville function n+1, n+2, so on until n+k. So obviously the number of sign patterns is the most to the k. So all the possible two values on k and length k. And Chowla conjecture predicts that in fact all of these patterns are realized at some point. So it's again another manifestation of this randomness. Every possible pattern that could occur should occur at some point, and in fact it should happen with the same probability, etc. And so this is a very basic statement about a very basic function, a fundamental function, like the Liouville function. And I like this because it kind of illustrates how little we knew about this. So even though it's a very natural statement, and looking at things over small intervals of the Liouville function is not an arbitrary product, as I mentioned, it's related to all these questions that we care about, we really know practically nothing about this just 10 years ago. So in fact, it was shown by Francis and Host using the Matomaki-Radziwill theorem, so after, that S of k grows faster than linear. So that's something that less than 10 years ago we were exploring. Even though how fundamental these kind of things are, we didn't even know that they grew at this linear. Then it was shown by McNamara that it grows quadratically, and Matomaki-Radziwill and Tao showed that it grows polynomially, so it grows faster than k to the a for any fixed choice of a. Now, as a consequence of the result of the previous slide, with an asterisk, clarify in a second. So it's not an entirely rigorous thing, but it should be rigorous in the future. You get, for example, the following consequence. Assume GRH. Then there exists some absolute constancy, independent, greater than 0, independent of k, such that the number of sign patterns of length k is at least 2 to the k to the z. So as you see, we didn't have a linear growth before, faster than linear growth before, and now we're getting kind of close to the exponential k, at least for the moment, assuming GRH. If you want an unconditional result, then from the previous result, you will get something like 2 to the log k squared, so it's still some sort of exponential behavior, but you see we're getting close to this basic thing. And, in a general audience kind of sense, this illustrates why GRH, so GRH is telling you that in the big interval, 1 and -1 appear essentially the same amount of times. The question here is on this little interval, what kind of patterns, how many of the patterns you get. So we didn't have the technology to move from information in big intervals to small intervals. That's kind of what we learned to do, how to do now. And now the important thing, why is there an asterisk? So this is not something that is yet rigorous. This is what will follow immediately from the results of the previous slide once they are proven for nilsequences. So the work is on a particular case of the uniformity case, but one should expect, what has a blueprint on how to extend these things to nilsequences. But as I said, the previous results are a few months old.
Is there a weaker thing you get without GRH in the first statement?
Yes, you get a 2 to the log k squared. And so you get this result. Well, and that I guess illustrates kind of what's the situation, how dramatic the progress has been in the last few years. And so let's move to a few words about the proof. So I'm not really going to tell you how the proof works, but what I really want to do is to give you kind of a summary of the general idea with the goal of explaining what is the abstraction that we have. So mainly I want to tell you what is it that we don't know. So hopefully taking the complement, what we know. So the strategy is as follows. We are dealing with a uniformity conjecture. Suppose the uniformity conjecture fails, which means that we can find many intervals, small intervals, x plus h, in the big interval 1 big X, where for each interval x that starts as x, we have some frequency alpha x, such that the Liouville function correlates with e to the 2 pi alpha xn in this interval. Correlation is big. The starting point of all approaches that we know this problem is that by the multiplicativity of the Liouville function, the frequencies that we're dealing with, the alpha x, they cannot really be independent, but must in fact satisfy certain relations with each other. So, an easy way to see this, which is not really, it's not rigorous, but it kind of is something similar to this, is if you look at some consecutive integers and you multiply them by a prime p, then you get a sequence of multiples, an arithmetic progression of multiples of p, right? And if you look at what happens with the values of the Liouville function, since it is completely multiplicative, the value at each prime is -1. And if you look at the sequence of values that you have here, when you multiply by a prime p, you get an arithmetic progression of multiples of p. It has essentially the same sequence of values, but inverted, multiplied by -1. So you get the same sequence, but each element multiplied by -1, so inverted. But this happens for every prime p. So for every prime p, you get an arithmetic progression of values that have the same sequence of values of the Liouville function in each case. They're all the original or multiplied by -1. And so you see that in a sense, what's happening here is related by multiplicativity to what is happening on this other place. And the reason why you have that these frequencies relate to each other is just only a slightly more complicated version of this basic observation. So the frequencies have these relations with each other. This is the starting point. The starting point in my own work is that it turns out that one can use these relations to kind of encode all the information about all these frequencies in a single object. So, and this turns out to be a useful thing to do. So what do I mean by this is that more precisely, what we can do is find a fixed large positive real number C. So by large, I mean that, if we are working in the interval from 1 up to big X, it has size small integers. It's outside the original interval. And the corresponding frequency alpha C with the following property. So this fixed element alpha C have the following property. For most of the original intervals, little x plus h, where we have an exceptional frequency alpha x, we can find primes, small primes, p1, pk of size at most h, such that C divided by these primes lands close to the initial point x of the interval, and simultaneously, the distinguished frequency alpha C multiplied by these primes lands close, mod 1, to the frequency alpha x that corresponds to this interval. So we have fixed C and alpha C distinguished elements, and for each interval x plus h, we can find a fixed choice of primes such that C divided by those primes is close to the initial point of the interval, and alpha C multiplied by those primes is close to the frequency mod 1. So in essence, what this is telling you is that these frequencies are synchronized in a very precise way, and synchronized in fact by one single element in a sense.
So there's some interval near x squared where some interval of x squared where the behavior and frequency where it's very bad, which causes all of these.
In principle, yes, but I guess the original way one will try to prove this is to prove that, but it's hard to do that. So one kind of shows that sort of like if there existed a frequency, it's more like that, it's down there. So you're dealing with multiplicative functions that could not even be defined in x squared. So it's like you do proceed by creating frequencies in other intervals outside the original interval, but in principle, the function cannot even be defined there. But it's more or less like that. Yeah. So you get that kind of all the behavior of these little frequencies comes from one element up there. And once you have this synchronization, this kind of global information, then it's not hard to prove the result using the Matomaki-Radziwill theorem there. Once you have this relation, you see that in fact it's not common, this happens, and in fact the only set of frequencies that can satisfy such synchronization are those that arise from functions of the form n to the it chi of n for some t and some character chi. And then once you have that, it's not hard to show that in fact the only possible counterexamples are the ones that one expects, which are the functions of this form n to the it chi. And this gives the result. Now this is a valid description of the strategy in a very high level term, but on the other hand, this strategy was introduced in an article 3 years ago, while the results were obtained a few months ago. So obviously there's something missing. And the reason is that the process by which one creates these special elements C alpha C is kind of delicate. They come from an iteration where you get information of the frequencies translated into frequencies on another interval and so on, and then you can do a domino. They use information on the original one. But this process is very delicate, and in original form, it breaks down as soon as h is somewhat small. The smaller h is, the more iterations you have to make to get the same set. When h is very small, this breaks down. So I'm not going to tell you much about how it works, but just to mention like a general idea, that the main point is that these frequencies alpha x turn out to enjoy much more symmetries than one might expect. So, there are the Fourier coefficients of general multiplicative functions in the sense of one should expect something bigger frequencies of symmetries, but there turn out to be a lot of things going on that one can exploit. For example, one thing they do is that they tend to cluster into small groups that satisfy some strong rigidity properties. So for example, there's like a genuine way of arranging them into little clusters And if you have, for example, two elements of one cluster related with elements of the other cluster, that automatically forces all the elements of one cluster to relate with all of the others. So there's all this kind of symmetries and rigidities that you can exploit. And once you take advantage of all those things, there's a way to actually carry out a more robust version of the previous process that succeeds in creating this distinguished pair C alpha C. So it's the same strategy, but a way to actually be able to carry that. So in the last minutes, let me tell you what I wanted to tell you, which is what is it that it's missing. So as I said, this strategy, what accomplishes is to reduce these problems, so essentially the three equivalent problems I mentioned before, to one specific kind of abstraction that is what we don't know now how to deal with. And it's for that that we use GRH. So what is this abstraction? Why do we need GRH? So the problem is as follows. So if the primes of size more or less h, so small primes that we care about, were to behave in a nice way, as GRH predicts, then we could deduce from that that for any fixed choice of C, we can guarantee that expressions of the force C divided by a product of small primes distribute well across the big interval, one big X that we are studying, and can thus in principle touch all or at least many of the intervals little x plus h that we care about. Otherwise, if primes were to behave badly, all this expression might actually concentrate just in a small part. Even if you look at every possible product of small primes, C divided by that will always concentrate on a small part of the big interval. And then this can only possibly give us information about a few of the frequencies of alpha x. So you see that the whole approach was based on the idea of finding these distinguished elements C alpha C, and then from that deducing, you have this synchronization and all these properties. And just when you're doing that, you're assuming one basic thing, which is that in fact, very concrete thing, that for each little x, each interval, so each initial point of the interval, you can find some product of primes, such as C divided by those primes lands close to x. So this looks like a much more pedestrian question, but it's the one thing that is missing. So either this or some, there's a lot of flexibility in the approach, so you need something at display. And this is, in a sense, every single abstraction that pops up in the argument is essentially of this form. This is the thing that we don't know how to deal with. So as you see, it looks like a simple question. It certainly is a question that has some physical space, so to speak. You're not dealing with anything having to do with frequencies or patterns or any other of flaws or anything. But we now, thanks to all the work in this last decades, we have all the machinery to transform this rather concrete information about, if we have this, if we knew how to get some sort of answer to this statement, then we have all the machinery to transform this into all the information about flows and frequencies and patterns that we were talking about before. And this looks like a much more, as I said, pedestrian question. So because of this, I think it's an exciting time to be working on this kind of problems, and hopefully we will see some substantial progress in the near future. Thank you.
Any questions? I have a question to Peter. So
He talks so fast. The only guy who talks faster than him is Zagier.
do you believe that within a reasonable time your original conjecture will be proved?
There's GRH there, it'll be proved as well. It looks close, yeah. Looks very close. I mean, he's using GRH, yeah.
No, not
in the logarithmic form. In the logarithmic form.
No, I mean your original one. Not...
Oh no, the original one. I should say something about twin primes, if I may.
Yeah.
This is a lot of the equivalence which tau proves is for the logarithmic form. The minute you take logarithmic form, you move away from trying to produce twin primes. There's averaging weights, early numbers. And in that sense, it avoids a parity, which Miguel was mentioning at the beginning, the parity difficulty that Selberg pointed to. So, but the conjecture was meant to be purely statistical without worrying about twin primes. So in that sense, this logarithmic form, which would give you entropy, is trying to prove that the lambda's got positive entropy. It's almost there. So I think that's in the cards, because you're allowed to use logarithmic. I think he's very close.
I guess that way with the tools we have now, even if we give approval of Chowla and your conjecture, it's still in a very similar way avoid the twin prime conjecture.
Yeah, right.
I think that objection applies even to the original.
Yeah, right. Yeah, the original one had no logs in it. It was stated just one point that I was confused about when you guys were working hard on this, all of you and the other group. So structurally, the enemy is null sequences. And this uniformity, and what you have to do in the null sequences, I always thought that already once you don't correlate against a null sequence, which is easy for a fixed null sequence, that's not difficult, that you should be done. But the point is that you have to take an inverse limit of null sequences, which is equivalent to this sub that you have to take on the inside. So the whole problem is this uniformity issue, which is hidden there. And if you assume a little more about the dynamics, that's what Host and Franz and Tychus do. That if you assume it's uniquely ergodic or countably many ergodic components, then you prove the full conjecture. And that's how that's gotten around. So I was just saying that because I was a bit confused about that point, but this completely clarified that. The star that this is being extended to null sequences is being done by the other theorem staff, that if you extend this to null sequence, that's, if I understand, your method is being used by others to extend it?
Yes.
So that will be a theorem soon. If I have a second, we're having a little reading group about his work, so anybody who wants to join in that, just stay off for 10 minutes. We've already started, but anybody's welcome to join in.
More questions? Okay, so let's thank our speaker again.